Welcome everybody to our PCAST talk for this month. So before we get started, we'll do just a little bit of news here about what's going on. So a few key dates. The PRIMA site visit is going to be taking place in May in Pasadena, and so the committee will be visiting JPL and looking at all of the preparations to show that PRIMA is on track and sort of ready for launch in the 2030s. PRIMA is also going to have a special session at the Summer AAS in Pasadena, California. So that will be sort of an hour-and-a-half session on one of the days from June 14th to 18th. This will feature hopefully a lot of the PRIMA team, since it will be in Pasadena, as well as some talks from the community and about how PRIMA will be available for sort of general observer use. And then we're anticipating at this point that probe selection will be occurring in late 2026. In the meantime, to keep getting your PRIMA fix, we're going to have a set of upcoming talks on PRIMA PI science. So coming up next month, April 27th, PRIMA affiliate Jed McKinney is going to be talking about the PRIMA science that can be done for the coevolution of black holes and galaxies. On May 18th, PRIMA affiliate Andrea Benzatti is going to be talking about the protoplanetary disk science. And then August 24th, Irene Shivai, who's also a PRIMA affiliate, is going to be talking about the dust and metallicity work. So today, of course, we have Rebecca Levy, and so she's going to be talking about sort of exciting prospects for work that could be done with PRIMA's FIRES instrument, looking at nearby galaxies.
Okay, let me share and hopefully it's still deciding to work. Okay, so hopefully you can see that screen all right. Okay, perfect. Great, yeah, so thanks for the invitation to give this talk and for y'all for calling in. So today I'm gonna talk about one of the science book cases that we put in for the PRIMA Volume 2 of the Geoscience book. But before I get to the PRIMA stuff, I'm going to talk a little bit about some exciting new results on the M81 group and M82. The science book paper was led by me, but in collaboration with Eric Kosh, Serena Cronin, Adams Mersina, and Nicole Melso. So just to give a brief sort of overview, first I'm going to focus on M82 Isus Primas, meaning M82 and its cousins. So giving some background on the M81 group and M82 in particular. And then I'll highlight some recent M82 results, especially from the JWST mission. And then towards the end, I'll talk about the unique abilities of PRIMA and how that will really revolutionize our ability to understand the ISM and CGM in nearby galaxies. Okay, so just to give everyone a brief overview of the M81 group and why it's so special and important. This group of galaxies is very nearby at a distance of only 3.6 megaparsecs. And it has something like 40 group members, some of which are circled here. And I know some of those circles appear empty, and that's because some of these galaxies are ultra diffuse or very faint. The sort of haze you see in this picture is all galactic cirrus, which I'll come back to talking about the challenges that poses and how PRIMA can help us with that. But of the sort of 40 group members in the M81 group, there are 3 sort of key major members shown here. They are M81, of course, after which the group is named. M81 is a Milky Way-like galaxy. It has a stellar mass that's very similar to the Milky Way. It has a modest star formation rate of just under about a solar mass per year. That's averaged over the last 100 million years. It hosts a low luminosity AGN in the center, and it's about solar metallicity. The next major member is M82, which we will talk much more about. M82 is a small galaxy. Its stellar mass is something like 3 × 10 to the 10. So between sort of LMC and Milky Way mass. It currently undergoing a starburst. So it has a star formation rate, again, averaged over the last 100 million years of 12 solar masses per year, so quite a bit higher than M81. It's also about solar metallicity. And it's a quite compact galaxy. It has a dynamical radius of only about 4 kiloparsecs, so it's quite small. And then there's a third galaxy, NGC 3077. This is an LMC mass object. has a very low star formation rate currently, and it's about 60% solar metallicity. And you can see from this gorgeous ground-based astrophotography image that these galaxies are interacting with one another. You can see it from the starlight alone. So these galaxies are in fact tidally interacting with one another. That is even more obvious when you look at the H1 emission in and around these galaxies. So that's what's being shown here in the colors now, is an overlay of the sort of tidally disturbed H1 in this system. And so to go through a little bit of what we know about the merger history of this system, the merger started about a year ago, so it's an early stage of the merger, and it's been relatively quiet so far. It's thought that M81 has accreted about 10 to the 9 solar masses of material and in stellar material, and that's been very metal poor, so only 6% solar. And this paper by Adams Messina from 2020 in particular was able to place a limit that the largest individual merger that has been accreted by M81 can't really be any more massive than the SMC. So again, the most massive thing M81 could have accreted so far is something like the SMC mass. The stellar halo of the M81 group, because of this sort of quiescent past, is extremely metal poor. It's one of the more metal poor stellar halos for a group of this size. But going forward, things are about to get really interesting for the M81 group. It has a dynamic future ahead of it. So it's thought that M81, M82, and NGC 3077 will fully merge in about 2 gigayears. And during that time, it will transform from one of the most metal-poor stellar halos to an incredibly metal-rich stellar halo with a halo stellar metallicity of something like 80 solar masses, or 80 solar masses, 80% solar metallicity. And that's primarily due to the large amount of metal-rich material that M82 in particular will contribute to that merger. So to sort of put the scale of the M81 group with some groups that people may be slightly more familiar with. So down here on the bottom right, M81 and M82 are separated currently by about 40 kiloparsecs. That's closer than the current separation between the Milky Way and the LMC, which is something like 50 kiloparsecs, and much, much closer than M31 and M33 are currently, which is 230 kiloparsecs. So sort of just to give a frame of how close these two galaxies are to one another, and sort of the timescales over which, again, we expect them to merge in about 2 gigayears. So I want to focus for the next few minutes here on M82 in particular. M82 is sort of the archetypal starburst galaxy, and this tidal interaction with its group members has triggered that starburst, and the starburst results from that. So many of these results that I'm going to talk about on this slide are from this really wonderful overview paper by Natasha Forster-Schreiber from 2003. So it's thought that a few 100 million years ago, somewhere between 100 million years and maybe like 250 million years ago, there was a major burst of star formation in M82 that was triggered by the close passage with M81. So in addition to triggering a starburst, it's also thought that this dynamical interaction set up the bar in this galaxy. It's hard to see because M82 is like perfectly edge on, but this galaxy does have a stellar bar with a bar length of about 1 kiloparsec. And bars are dynamic features, and so it's thought that the bar was formed about 100 million years ago or so. Much more recently, there have been 2 more recent vigorous bursts of star formation that are responsible for sort of the most recent young stellar clusters that are formed, as well as the spectacular outflow from this galaxy. So about 10 million years ago, there was a burst of star formation peaking at about 160 solar masses per year that occurred throughout the central 500 or so parsecs, but it was really concentrated in the very center. But again, the burst was 500 parsecs, but the disk isn't really that big. So really a global starburst in that case. That burst probably lasted a few million years. And then shortly thereafter, only 5 million years ago, M82 underwent a second burst of star formation This was concentrated in its circumnuclear ring, which has a radius of about 100 parsecs, and in the stellar bar. And that was much more mild, peaking at about 40 solar masses per year of star formation. And then again, that has sort of lasted a few million years. And it's back to a slightly more quiescent state, although it's still something like 10 solar masses per year of star formation, which is far from quiescent. First has resulted in a spectacular multi-phase galaxy-scale superwind. The image I'm showing here is an H-alpha image from Linz and Sandage 1963, which was the discovery of the M82's outflow. They called it an explosion, which isn't, maybe too far off from the truth there. And of course, the M82 and its outflow have been studied by many, 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 many people in the decades since the famous Linz and Sandage discovery. So we know that the outflow of M82 extends out to at least 11 kiloparsecs from M82's disk. And that's seen from this feature that's called the H-alpha cap. It's this filament of material 11 kiloparsecs away. It's seen in H-alpha, it's seen in the X-rays, and it's thought that this is evidence of a past outflow activity in M82, likely from one of those earlier bursts of star formation. So it is thought that the cap is kinematically connected with the outflow of M82. But it turns out the outflow of M82 may extend even further. So recently, a couple years ago, there was this paper by Lockhorst et al. Using the Dragonfly array, looking at H-alpha, and they found this H-alpha shell. It's a little faint here, but there's this shell of H-alpha emission about 40 kiloparsecs from M82. And if that is, evidence of past outflow activity, or evidence that at least the outflow has reached that far, then it's possible that M82's outflow is, quite far-reaching from its disk, especially given the size of M82's disk. So I wanted to take everyone through sort of a multi-wavelength gallery of what M82 looks like at various wavelengths because it has been studied so much. So this is one of my favorite images of this beautiful multi-wavelength color composite showing X-ray data, optical data, and Spitzer data looking at the dust. M82's outflow glows brightly in X-rays. This is mostly thermal X-ray emission. So there's a lot of very hot gas, million degree Kelvin gas being expelled from the center of this galaxy. I didn't say it explicitly, but M82 does not have an AGN. And so again, all of this X-ray emitting material is being launched from this starburst and escaping outward. M82 is of course also visible in the ultraviolet. It has been studied in the optical, as shown by this incredible multi-wavelength Hubble image that I'm sure folks on this call have seen before. Its outflow is incredibly prominent in, well, at all wavelengths, but especially in the near and mid-infrared. This is data from Spitzer. One of the things that makes M82's outflow so unique is generally outflows from galaxies are quite faint and hard to detect. M82's is extremely prominent. You can't miss it. And so in that regard, M82 and its outflow are very unique. There's not really any other systems that have an outflow as prominent and as large relative to the galaxy as M82. This is a gorgeous submillimeter image of M82 looking at CO 1 to 0 from NOEMA, showing the sort of filaments and the tidally disrupted nature of the disk of M82. And again, the CO here does appear in the outflow, but it's much more concentrated in the disk, and again, sort of in these larger scale tidal streamers and features. I will just advertise that there is more data on M82 coming from the SMA. Jakob Den Brock is working on a publication doing a spectral line survey. Maria Jesus Jimenez Donaire has some gorgeous high resolution data looking at the young massive star clusters. And Eric Koch and Jakob den Broek have other large SMA programs on M82, so stay tuned for much more submillimeter data on this galaxy coming shortly. And then the last image to show here is the radio image. This is looking at the H1 emission from the VLA, and it looks like a mess. The white dashed line here is showing the orientation of the disk, and you can clearly see you don't really see the disk very well in the H1. You can see the outflow, but it is so widespread and just a kinematic mess that's happening in this galaxy. So the outflow and the M82 itself change appearance quite a lot as you go to different wavelengths. So I haven't talked at all yet about JWST, but of course there are JWST observations of M82, and so I wanted to highlight some of the data and the programs that have looked at M82 thus far with JWST, and then go through some of the science results from that, because it has really revolutionized our view of M82. So in terms of imaging from JWST, Project 1701, which is PI'd by Alberto Bellato and with which I'm involved, this cycle 1 program looked at this part along the minor axis of M82 using NIRCam in 6 filters from 1.4 microns to 3.6 microns. Adams Messina has a cycle 3 program looking at sort of the entire disk and outflow region of M82, focusing on the filters listed here, and mostly studying the sort of halo stellar population. From that same cycle 1 program that I'm heavily involved with, we also got MIRI imaging at 5.6, 7.7, and 11.3 microns. And then Sylvain Veilleux has a cycle 3 program looking at this portion of the southern side of the outflow in 2 more longer wavelength MIRI bands. In addition to the imaging, there have also been spectroscopic efforts in M82. So in cycle 1, Eigen Lee had a program using the NIRSpec MSA from 3 to 5 microns at moderate spectral resolution, using the MSA as to do sort of this long slit spectroscopy on the disk and out into the outflow. Very recently and excitingly, Serena Cronin, who's a graduate student at the University of Maryland, got a cycle 5 program on M82 using NIRSpec's MSA from 1.7 to 5 microns using its high resolution mode. And she put these little tiny slits shown here in green. She placed those over prominent dust filaments along the outflow. And so we'll get RF 2700 spectroscopy in all of these little regions to really be able to trace the kinematics of the outflow very well. So we're super excited for her program and looking forward to those data. And as part of that same cycle 1 program that I'm involved with, we also obtained MIRI MRS data from 5 to 28 microns in the very center of this galaxy, focusing on where most of the massive star clusters are. So I wanted to show some of the beautiful imaging data that we've attained as part of this cycle 1 program. So again, here's sort of that multi-wavelength color composite of M82. Our NIRCam data of this galaxy are just truly mind-boggling. So this is a 6-color composite image of all of our NIRCam filters. This was put together for us by the lovely folks at the ESA Web, because this image and the next one I'll show were the JWST pictures of the month in June of 2025. So in this image, you can see the disk here in the center, and all of the red, orange colors are dust, small H's, polycyclic aromatic hydrocarbons, in the outflow of M82, showing this incredible filamentary and bubbly structure as you go from sort of these linear filaments very close to the disk midplane to this much more sort of fluffy, bubbly structure as you get away from the galaxy disk. The dust in the outflow is even more prominent when you look at our MIRI data. So this is a 3-color composite of our 3 MIRI filters, all of which contain PAH features in them. And so again, you can see this sort of linear filamentary features close to the disk, and then just a wild amount of dust being expelled from this galaxy by the starburst. In addition to the outflow of this galaxy, we can zoom into the very center where the central starburst is concentrated. So this is an HST image from NICMOS at 1.6 microns. And the resolution and sensitivity of JWST have just fundamentally given us a new view of the central starburst in this galaxy. Just the detail that you can see is truly mind-blowing to me, at least. I'll note that all of the white dots in this image, that's not noise, those are all stars. And so JWST, in addition to letting us study the massive star clusters, allows us to do resolved stellar population analyses like we can do in the local group out to things like the M81 group now, which is really awesome. And I'll again just advertise that this image and some other images like this were part of a NASA press release that went along with the publication of our first paper from this collaboration. So I want to highlight some of the M82 results that have come out from our team. I'm not going to go through all of these, but I did want to especially highlight that many of the papers on M82 from our team have been led by junior folks and continue to be led by junior folks. So many of these papers are concentrated on the outflow, although we do have my paper and a paper with a student that I've been working with that are concentrating on the young massive star clusters. So to go through a few of these results quickly, using the NIRCam imaging data in the center of M82, we were able to detect over 1,300 massive star clusters in the central kiloparsec of this galaxy. So by massive here, I mean anything that has a stellar mass greater than 10 to the 4 solar masses, assuming an age of 0 million years, so assuming a zero-age main sequence population. If the star clusters are actually a bit older than that, more like 8 million years, the number of massive star clusters drops by about half. But regardless, there are several hundred massive 10 to the 4 solar mass star clusters in the central kiloparsec of M82. Just for some context, 30 Doradus in the Large Magellanic Cloud, which is the most sort of extreme star forming region in the Milky Way group, has a stellar mass of just over 10 to the 4 solar masses. And so the center of M82 harbors several hundred 30 Doraduses, which is what makes it an extreme starburst. So compared to the previously defined Hubble star cluster catalog, the star clusters that we have found with JWST and NIRCam specifically, almost all of them are new, meaning they didn't show up in the HST catalog. That's sort of illustrated by these panels down here. On the left, I'm showing the JWST image. On the right is the Hubble image. Things that are circled in pink are star clusters that are only possible or only visible in the NIRCam images. The light blue circles in the HST side show the original HST catalog. And then the sort of darker blue circles show those star clusters that we see both with NIRCam and with HST. And so you can see that the slightly longer wavelength range of NIRCam lets us see through the dust better than you can do with HST. And so we detect star clusters, massive star clusters like these three in particular, that just simply aren't visible with HST because of the extinction. The sort of flip side of that statistic of most of the star clusters that we find are new is that of the clusters that were detected with HST, we only detect about half of them in our NIRCam catalog. And that's not because all of a sudden, star clusters don't emit in the near infrared if they emit in the optical. It's that the increased angular resolution of NIRCam means that things that to Hubble, which used to look like massive individual clusters, break apart into many substructures that no longer meet our criteria for massive star clusters. So it used to be, sort of monolithic looking things, rapidly fragments and breaks apart. And so this is why we don't recover all of the HST clusters It's not that they are not emitting there, it's just that they're maybe not quite as massive as we thought that they were. So we have an incredible multi-wavelength catalog now of where all of the massive star clusters and massive star cluster candidates are in the center of M82. So this is work in preparation that I did with a summer student this past summer, Melnick Niebert, who's currently an undergraduate at Columbia University and worked with me at Space Telescope last summer. He cataloged all of these star clusters that we see in our MIRI images in the center of M82. And then we cross-matched their locations with the cluster catalogs from the optical, the near-infrared, and the submillimeter, as well as in the mid-infrared. And the question we wanted to ask is how many unique individual star clusters are there actually? So if you look at, every wavelength that a star cluster should, emit over, how many physical star clusters are there? And the punchline is that there's about 1,100 individual massive star cluster candidates in the central 600 by 600 parsecs of M82, which is quite a few of them. So this work, we're currently writing it up, so stay tuned for this paper coming out hopefully soon. I want to transition from talking about the massive star clusters to talking about the superwind, because it is one of M82's defining characteristics. And again, thanks to the wealth of multi-wavelength data, we are able to use the new JWST data in concert with much of this previous data. And so one of the first results that came out of our group was led by Deanne Fisher, who showed that the 3.3 micron emitting PAHs, which are the sort of smallest, most fragile PAHs in the JWST bands, those PAHs avoid where the X-rays are the strongest. So these two panels show cuts across the northern side of the outflow and the southern side of the outflow. The black curves show the PAH emission, and the blue curves show the X-ray emission. And so you can see that where the PAH emission is the strongest, where we have these sort of filaments, is not where the X-rays are strong. In fact, the X-rays peak in between those regions. This sort of makes sense that the PAHs should not survive in those regions of harsh, hot material, but it's nice to sort of see it in the data directly. One of the puzzles that came out of this first analysis, however, was that if you look at the correlation between the PAHs, again in the black curves, and the Paschen alpha, which is tracing the ionized gas, shown here in the red curves, those line up with one another very well. And so it was kind of surprising that the small fragile PAHs are highly correlated with the ionized gas. That was unexpected, that you would be able to have them survive in regions that are hot enough to ionize hydrogen. This is what we saw for sort of the base of the superwind, so very close, within 200 parsecs of away from the midplane. We've since repeated some of this analysis in a more spatially resolved way. So this was work that was led by Sebastian Lopez, and this was also sort of first done by Vicente Villanueva. So what this first panel or column is showing is on the x-axis, you're looking at the PAH emission and how that correlates with the CO emission on the y-axis in 3 different bins of distance from the midplane. So this top row is showing things that are within a kiloparsec from the midplane. This middle row is things that are 1 to 2 kiloparsecs from the midplane, and then the bottom row is out to above 2, but out to 3 kiloparsecs from the midplane. And so what you see here is that in all of these distance bins, above and below the midplane, the PAH emission at 7.7 microns is strongly correlated with the CO. Again, this is not unexpected. The PAH emission should be tracing cool neutral material, and the CO is also tracing cold molecular neutral material. In the center column here, I'm now showing the correlations with H alpha. So again, tracing the correlations between the ionized gas and the PAHs. And we recovered that same trend that the PAHs are highly correlated with the ionized gas. Definitely within 2 kiloparsecs, this trend flattens a bit when you get out a little bit further. And when we look at the correlation with the X-rays, there is, some weak correlation between the X-rays close to the midplane, but that is, completely gone by the time you get out to about above 2 kiloparsecs. Those phases have decoupled. And again, the PAHs are sort of avoiding, not able to survive in regions where the X-rays are strong out further away from the midplane. Okay. So what's going on here? Why did the PAHs correspond so closely to the ionized gas? Well, if we zoom in and we look on small scales, the PAHs are in clouds. You can sort of see some examples of these little cloud-like structures of PAHs here, and in fact, they agree quite well with what one would expect from simulations of PAHs and dust entrained in galactic outflows. So what we think is going on here is that the PAH emission is arising from the photoionized surfaces of neutral clouds. So if we could zoom in and we had, infinite resolution CO and H1 data, we would see that those phases are also in these cloud-like structures. And as those neutral clouds are, propagating through this hot X-ray emitting plasma in the wind, the surfaces of those clouds become photoionized. And that's also where the dusty PAH material is. And so we're seeing the ionized surfaces of these clouds, which is then why the ionized gas tracers like Paschen alpha and H alpha appear so tightly correlated with the PAHs and the neutral material, because they're coming from the same structures. So I kind of alluded to this a little bit in talking about the correlations between the X-ray emitting gas and the PAHs. But a work led by Serena Cronin that has been submitted, so hopefully will be out on the archive very soon, is looking at which PAHs can actually survive in the wind. So the figure on the right is showing some model grids using the Drain et al. 2021 dust models. And on the x-axis, we're showing the ratio between the 3.3 micron emitting PAH and the 11.3 micron PAH. And on the y-axis is the ratio of the 11.3 micron PAH to the 7.7. And in this parameter space, the vertical axis mostly traces the ionization state of the pause, where more neutral pause will be up towards the top of this diagram and more ionized pause will be down towards the bottom. And the x-axis mostly traces pause size. So large pause are to the left and then smaller pause are to the right. The 3 different colored grids that you're seeing are 3 different estimates of the UV radiation field. So just sort of showing how this changes slightly with the radiation field. And so what we can do with our data is we can make these exact ratio maps in a spatially resolved way. And so on the left here is that 3.3 to 7.7 micron PAH map. And on the right is the 3.3 to 11.3 micron PAH map. And I'm now realizing that I included the wrong one. Apologies that I don't actually have the y-axis here. And so we can look at where the actual data from M82 and its outflow fall in this diagram. And what we can see is that most of the points tend to cluster down here towards more ionized and large PAHs. In fact, the color scale here, which again, I have forgotten to include the color bar, I apologize, shows distance from the midplane, where redder objects are further from the midplane and blue are closer to the midplane. And so the conclusion, one of the conclusions from this paper is that the pause tend to be larger and more neutral as you get out further from the outflow, because those are the ones that can survive getting out of the starburst itself. The small pause tend to be found very close to the midplane, very close to the starburst, because they're destroyed quickly in the harsh wind environment. But the large neutral ones are big enough to start out with, that they're the ones that can more easily survive out to larger distances from the midplane. So those are just sort of a whirlwind highlight of some of the new JWST results that are coming out. But I want to switch gears to talk about the far infrared, because there has been a lot of work done on the far infrared in M82. So these are some images from Herschel Pax showing some far infrared fine structure lines. And I'm sure, as we all know, the far infrared is incredibly important. It has these really important diagnostic lines that are the main heating and cooling channels of the ISM. They can reveal the multi-phase nature of the superwind. They can, of course, give us kinematics. Polarization information gives us details about the magnetic field. They constrain the radiation field. There are so many things that the far infrared is used for to understand the sort of processing and heating and cooling in the ISM and circumgalactic medium. So for the magnetic field, I wanted to show this gorgeous image from Borloff et al. 2023, who used SOFIA Hawk Plus to measure the magnetic field in the far infrared. And you can see the magnetic field lines sort of overlaid on this image. SOFIA was also used in the far infrared, so SOFIA upgrade. I was able to make a map in C++ of the center of this galaxy and some pointings along the outflow. So this is showing in the center of the galaxy along the midplane. This is the peak intensity of the C+ 158 micron line, which is the major cooling channel of the ISM, and it's also one of the brightest line in the far infrared. And we were able to, in addition to detecting this line in the midplane, we also detected it along the outflow. So in these sort of 7 pointings down on the southern side of this galaxy. The teal spectra here show our upgrade C+ spectra in each of those little footprints. So going from kiloparsec away from the disk out to nearly 2 kiloparsecs from the disk, we were able to not only detect the C+ line, but use the kinematic information in comparison with existing CO and H1 data, to show that most of the C+ in the outflow of M82 is associated with the neutral phase of the ISM. So these are just, again, some highlights. There's been much, much more done in the far infrared on M82, but looking towards the future of what PRIMA will enable us to do. So we wrote a science book case to focus on spectroscopically mapping the entire M81 group. So on the left here, I'm showing the background grayscale image is from Palomar, but the inset here is from Subaru from Adams Messina's 2020 paper, again showing the 3 major players in the M81 group, as well as some of the sort of intervening material. On the right again is the H1 map, again showing the neutral gas that's being tidally disrupted in and around these galaxies. The white squares overlaid on these images show a 100 kiloparsec by 100 kiloparsec region, which captures all 3 of these galaxies and there's sort of tidal debris around them. So to spectroscopically map this entire region, we can use the FIRES instrument on PRIMA, and in particular the high spectral resolution mode, which allows us to cover the entire far infrared wavelength range from 24 microns to 235 microns at velocity resolution good enough to do kinematics 15 to 150 kilometers per second in only 170 hours, which is a long time, but it is totally unattainable any other way to get that kind of high spectral resolution and complete wavelength coverage over such a large area. And so this was really exciting when we discovered that this was actually feasible. And in particular, many studies before that have focused on this group have really focused on M82 itself, even getting things like out to the cap which I'm highlighting here. This is the X-ray image of M82 and the cap up here, which is that outflow feature that's 11 kiloparsecs away from the disk of M82. Even getting that full, complete spatial coverage between those two tends to be really hard, just because that's a large area to cover. At the distance of this galaxy, 11 kiloparsecs is about 11 arc minutes, so quite a large area to cover. So in addition to the spatial coverage that this will get, I think really what's super exciting to me is the spectral coverage. So this is an image from our science bookcase showing the black curve in the background is a far infrared SED of M82, or actually several of them that have been stitched together. So you can see the rich spectral information that's already visible in the spectrum. And so some of the key diagnostics that we'll be able to get with PHI-RES, the bands of PHI-RES are shown in the purple shading, again from 24 to 235 microns. And there are these lines that tell us about every phase of the ISM, from the ionized to the molecular and everything in between. And so it's this rich spectral information that we will have across this entire region that is really the transformative power of something like PRIMA, and especially with the PHI-RES FTM mode. So again, just to sort of reiterate, we can get maps like what was done with Herschel-Pax, so all of these important spectral diagnostics, but not just in and around M82, over this entire 100 kiloparsec by 100 kiloparsec region, and in many, 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 many more lines as well. And so that 170 hours, what do you get there? The way that we calculated that was, to map this entire region, we want to detect the C+ line in the tidal streamers with a signal to noise of more than 1,000, because that will ensure that we can get these weaker but still very important lines. And so we will have robust detections of these really important diagnostics of the ISM heating and cooling and radiation field and kinematics, etc., over this entire region, for a large program, but that will have incredible legacy value for the community going forward. This will really be an unparalleled data set. So with that, I will leave my summary slide up. I've put a link to our science bookcase if you'd like to read it. And with that, I'm happy to take questions. Thank you all.
Awesome. Thank you so much, Becca. So we can take questions in the chat, or if folks just want to speak up or raise hands.
Yeah, Betsy, I don't think I can see the chat. So if there is anything, if you could.
Yes, I will let you know. I don't see anything at this point. So I wanted to ask too, I mean, PRIMA is so fast. Obviously, the M81 group is extremely exciting. What would sort of like your second target be? Like, what would like your second choice area be for mapping?
Yeah, so I'm sure you can guess what I'm going to say, but the other sort of canonical starburst galaxy in the local universe is NGC 253. It is not in a merger. So it's a starburst, but it's a different phenomenon. And so that would certainly be the other science book case I had thought about putting in if in addition to this one, if I had time, would be sort of mapping all of the local starbursts. So again, starburst galaxies are really important. They give us a nearby window into how star formation may have proceeded, at earlier times in cosmic history. And so I think studying, the details of their ISM and CGM heating and cooling with something like PRIMA is, definitely worthwhile doing. And again, with the fast mapping speeds, you can get many starburst galaxies in a, modest amount of time.
Yeah, I mean, I guess I was just wondering, I mean, even if it's not sort of known to be interacting, like if there's a case for even just mapping like its group or mapping some of these other nearby groups to sort of look for more of these types of extra planar gas. I think it's some of the exciting stuff that I've seen from like the M82 wind and the NGC 253 wind is just like how far out this goes, right? And sort of like how much one can get into the real surroundings of these galaxies.
Yeah, for sure. And there's a huge question also about how, if the gas is actually making it out into the CGM or whether it's like raining back down onto the disk. Potentially triggering more star formation in the future. Those signals are really hard to find, but they are certainly worth looking for with something as sensitive and with the kinematic information that something like PRIMA gives you. So yeah, absolutely.
Very cool. All right, folks. Well, if there are no other questions, thank you again, Becca. And join us again next month for our next talk, and take care, everyone.
Great.